Hysteresis loss and eddy current loss are two critical phenomena in electrical systems that contribute to energy losses and inefficiencies. Understanding these losses is essential in the design and operation of electrical devices, particularly transformers and motors. Hysteresis loss occurs due to the lagging magnetization and demagnetization of the core material, while eddy current loss results from the induction of circulating currents in conductive materials exposed to a changing magnetic field. By delving into the mechanisms of hysteresis and eddy current losses, engineers can optimize the performance and efficiency of electrical equipment. Hysteresis loss, also known as magnetic hysteresis loss, is a type of energy loss that occurs in ferromagnetic materials when they are subjected to a varying magnetic field. This loss is a result of the lagging of the magnetic flux density behind the magnetizing force when the magnetic field is alternated. In simpler terms, hysteresis loss is the energy dissipated in the form of heat when the magnetic material repeatedly magnetizes and demagnetizes in response to changes in the applied magnetic field. The hysteresis loop, which represents the relationship between the magnetic flux density and the magnetizing force, shows the energy losses that occur within the material during each cycle of magnetization. The area enclosed by this loop represents the hysteresis loss, and it is proportional to the frequency and magnitude of the magnetic field changes. In practical applications, hysteresis loss is a crucial consideration in the design of transformers, electric motors, and other devices that involve magnetic materials. Minimizing hysteresis loss is essential for enhancing the efficiency and performance of these systems. The formula to calculate hysteresis loss in a magnetic material is given by P_text equals K_H times F times B_text max text N times V, where is the hysteresis loss, is the Steinmetz hysteresis coefficient, is the frequency of the magnetic field in Hertz, is the maximum magnetic flux density in Teslas, is the Steinmetz exponent, is the volume of the magnetic material. The hysteresis loss formula considers the frequency of the magnetic field, the maximum magnetic flux density, the material's volume, and the hysteresis coefficient to determine the energy losses due to hysteresis in the material. It's important to note that the Steinmetz hysteresis coefficient and the Steinmetz exponent are material-specific parameters that characterize the hysteresis behavior of the material. These values are determined experimentally and may vary depending on the type of magnetic material used. Eddy current losses, also known as eddy current heating or simply eddy losses, are a type of energy loss that occurs in conductive materials when they are exposed to a changing magnetic field. These losses result from the induction of circulating currents, known as eddy currents, within the material. When a conductive material is placed in a varying magnetic field, such as the core of a transformer or the rotor of an electric motor, eddy currents are induced due to Faraday's law of electromagnetic induction. These eddy currents circulate within the material, creating loops of current that generate heat through electrical resistance. This heat dissipates energy and contributes to efficiency losses in the system. Eddy current losses are proportional to the square of the current flowing through the material and the electrical resistance of the material. To reduce eddy current losses, engineers often use laminated or segmented cores made of materials with high electrical resistivity to limit the circulation of eddy currents and minimize energy wastage. In summary, eddy current losses are an important consideration in the design of electrical devices, and mitigating these losses is essential for improving the efficiency and performance of transformers, generators, and other electromagnetic systems. The formula to calculate eddy current losses in a conductive material exposed to a changing magnetic field is given by P_text eddy equals K_E times FA times B_text max me times V, where is the eddy current loss, is the material dependent constant for eddy current loss, is the frequency of the magnetic field in Hertz, Is the maximum magnetic flux density in Teslas? Is the thickness of the conducting material? Is the volume of the conducting material? The eddy current loss formula takes into account the frequency of the magnetic field, the maximum magnetic flux density, the thickness of the conducting material, and the material-dependent constant to determine the energy losses due to eddy currents circulating in the material. It's important to note that the material-dependent constant for eddy current loss varies depending on the material properties and the geometry of the conductor. Additionally, the thickness of the conducting material plays a significant role in determining the eddy current losses, as thicker materials result in higher losses due to increased resistance to the circulating currents. In conclusion, hysteresis loss and eddy current loss are two significant sources of energy dissipation in electrical systems involving magnetic materials and conductive materials, respectively. Hysteresis loss. Hysteresis loss occurs in ferromagnetic materials due to the lagging magnetization and demagnetization in response to a changing magnetic field. This loss results in energy being converted into heat as the material repeatedly undergoes magnetization cycles. Minimizing hysteresis loss is crucial for enhancing the efficiency of transformers, motors, and other electromagnetic devices. Eddy current loss. Eddy current loss arises in conductive materials when exposed to a varying magnetic field, inducing circulating currents known as eddy currents. These currents generate heat through electrical resistance, leading to energy losses in the material. Design considerations such as using laminated cores and materials with high electrical resistivity can help mitigate eddy current losses and improve system efficiency. Understanding and managing hysteresis and eddy current losses are essential for optimizing the performance and efficiency of electrical equipment. By employing appropriate design strategies and material selection, engineers can reduce energy wastage due to these phenomena and enhance the overall effectiveness of electromagnetic systems.